Hello and welcome back. Now this video on the introduction to surface integrals on manifolds using differential forms. Now surface integrals on manifolds using differential forms provide a modern coordinate-free way to integrate over surfaces or higher dimensional manifolds in differential geometry. This framework generalizes classical notions of surface integrals in vector calculus and is deeply tied to the language of differential forms, the exterior calculus and Stokes theorem. All right, now before I go any further, there's a video in the playlist immediately preceding this which looks at the surface embedded in 3 dimensions, and it looks at parameterizing as a 2-dimensional surface embedded in a 3-dimensional manifold. And that is, you should see that video first before seeing this one. That's an example upon which I'll build the general case. So please, before you watch this video, please go back to that one and have a look. Was it surface integrals or something, or manifolds in 2 dimension or something, I think it's called. But it's the video that immediately precedes this one in the playlist. This is the general case, and that one goes back to 2-dimensional surfaces. All right, and I may during this video just refer to it from time to time. All right, so perhaps it'd be a good idea to hide that. All right, so let's look at our setup. So we let M be an n-dimensional smooth manifold. For simplicity, we'll assume that the set S is the surface S is contained in the manifold M is a smooth-oriented k-dimensional submanifold, e.g. a 2D surface embedded in R3, as I was just speaking a minute or so ago about, or a higher dimensional surface in Rn. So this video is about the general case. But in the last video, I looked at this using this surface here and one other, and I looked at the surface integral involving this 2-dimensional surface embedded in 3-dimensional in R3. All right, and this video is about surfaces of arbitrary dimension embedded in Rn, again where n is arbitrary. Okay, so we have our surface S here in Rk, and it is a submanifold to M. Okay, M is an n-dimensional smooth manifold, and S is a smooth-oriented k-dimensional submanifold. All right. So the question later on in this video will come up about why is k equal to or less than n, and so on. Anyway, let's move on. All right, so differential k form, on M is an antisymmetric multilinear map that acts on k tuples of tangent vectors and produces a real number. So omega here belongs to the space of k forms on M, and it's a map, k times the tangent space there to the reals. It takes vectors from the tangent space to the manifold M at P and takes k of them because it's a k form and maps them to the reals. All right. I've been over that many times in past videos. So differential forms provide a natural way to generalize the concept of volume or flux over a gradient. Go back to near the beginning of the playlist and I look at the one form as a gradient, or the gradient as a one form, I should say. Now, surface integral of a differential form. The surface integral of a k form omega over an oriented k-dimensional submanifold S of M is defined as the integral of omega over S. Okay, obviously I'm going to do more than that, but that's just a starting point. So the surface integral of a k-form omega over an oriented k-dimensional submanifold S of M is what you'd expect it to be. All right, so let's have a look for local coordinates for omega on M. So M is an n-dimensional manifold and omega be a k-form on M, where k is equal to or less than n. Now suppose we have local coordinates x1, x2, xn on M, and I'll show you a diagram of that before long. The k form, omega, can be expressed in terms of these coordinates as, so this omega on M, okay, is the sum over these different values of ik here. And what this means is here, these q, I1, I2 up to ik, which is a function of x1 to xn, maybe not all of them, all right, because it's k dimension, it's less than n, and these are the basis 1 forms, the xi's. Now, you could have here, what this means is that these q's, as a function of the x1, xn coordinates on M, are smooth functions on M. So if you go back to the last video, I had an example where I was dealing with 2 forms, and omega was In one case, it was Q of XYZ times the 2 form dx wedge dy plus, then it was Q was a function of maybe 1 or 2 or 3 of those coordinates times the wedge product dy wedge dz, right? And then there was another element, a Q of so many variables times the wedge product dz or dx wedge dz. Okay, and you can see that, so you can have a linear combination of these. That's what the sigma is trying to get at. Okay, K will be the dimension of the submanifold, N is the dimension of the manifold in which the surface is embedded. So K is the dimension of the surface that we're talking about, whatever dimension we're in. In the last video, K was 2 and N was 3. This time round, we're just talking about the general case where you have an n-dimensional manifold and a k-dimension submanifold. The x, I1 wedge, so on and so on, are the wedge products of the coordinate basis 1 forms. And so I've already brought up this question, so why is k equal to less than n? Well, by definition, a k-dimensional surface S embedded in an n-dimensional manifold cannot have a dimension k greater than n. All right. So this is because the surface S locally sits inside M, and the number of independent directions or dimensions on S cannot exceed the dimensions of the ambient space M. If you think back where we had a moment ago, we had that surface, that green one, embedded in R3. Well, K cannot be anything more than N. I mean, the ambient space itself, R3, has 3 dimensions, that's it. So the surface itself can't be more than that. But, okay, I think for obvious reasons there. A differential K form on M is constructed using wedge products of K differentials dxi. This is a K form. And there are only n coordinate differentials, dx1 up to dxn, available. If K is greater than n, any wedge product of more than n differentials would automatically be 0 because the wedge product is antisymmetric. You've only got up to n. If you start repeating dx1, wedge all that, then dx1 again, the whole thing goes to 0. So, okay, because of the antisymmetry of the wedge product. Hence, for a non-trivial K form to exist, K must be at most n. If K equals n, the K form being integrated is an n form, which is the top dimensional form on M. So integrating an n form corresponds to computing a volume on the manifold. We're interested in the case where it's less, where K is less than n. All right, so let's get a little bit more specific. So let's talk now, we'll get ultimately to the pullback to local coordinates. But anyway, let's step back before the pullback. Let's let S, our surface S, be over here, surface S on the manifold M. This is our submanifold here. Okay, let it be parameterized by a smooth injective one-to-one map. So F is a map from the open set U contained in RK to S contained in M, to the set S contained in M. And F is parameterized. F is a function of U1, U2, U3, UK coordinates on U. Okay, and that's equal to here x1, a function of those same U coordinates again, x2, a function of those U coordinates, all the way up to xn, a function of those U coordinates. Okay, under this map, that is F that takes points here in U and maps them to points here in S. All right, where U is an open subset of RK. All right, now the pullback. So the pullback, F upper asterisk of omega on U, is expressed in terms of the parameters U1, U2, UK of U. In local coordinates, if F is given by this, and then this gives you the coordinates of your surface over here on M, all right, then the pullback, using the formula earlier, was, and as in the previous video, was the pullback of omega under the map F is then this, and where the Q is, where we substitute in this map F of U1 to UK times the determinant of this times the wedge product of the coordinates in the U system. So the integral of omega over S, we can point out the integral of omega over S, remember the K form on the submanifold on M, in the submanifold S, the submanifold S in M, right, can then be pulled back. So it becomes an integral over the set U, and we integrate the pullback of omega under the map F, and it's this object here that we integrate, as in the last video, and as in all the other videos in the pullback series. All right. So what's happening now? Here's our open set U. Here's a point P, mapped to a point F of P under this map here. Takes points in the open set U contained in RK, whatever K is, and maps it to the surface S contained in M, submanifold S contained in M. All right. And in S contained in M, we have these coordinates. All right. Okay. From which, but remembering that this is RK, this is k-dimensional submanifold, this is an n-dimensional manifold, the M here. Now, at any point in S, we have the cotangent space here in which our k-forms exist. Here it is at the point F of P. The point P here is entirely random, so it could be anywhere in here, so same thing with F of P. It's entirely arbitrary, I should say. The cotangent space to the set U at the point P is shown here. All right. And what the pullback does is it takes the K form here and pulls it back to a K form over here. That's the point of that. This F upper asterisk omega is the pullback of the K form omega from here, from this cotangent space, pulling it back to here. All right, so pulling back the K forms from this submanifold to this open set here. All right, the T upper asterisk, so this is the cotangent or dual space to the manifold U at the point P, and this is the cotangent space to S at the point F of P. That's what notation they're saying. All right, so orientation, just a note on that, we should say. So the orientation of S is critical for defining surface integrals. Because remember, I won't get into that, but I was going to talk about sign values and so on, but I'll leave it for the moment. A k-dimensional manifold S is orientable if it admits a globally consistent choice of direction. Think right-hand rule. In local coordinates, this orientation determines the sign of du1 wedge du2 wedge all the way up to wedge duk. So, for example, integrating a two-form omega equals k dx wedge dy depends on whether S is oriented outward, positive, or inward, negative. If dx wedge dy is chosen, the orientation follows the right-hand rule for xy. Okay, so if we choose dx wedge dy, then the orientation follows the right-hand rule for xy. Choosing the opposite orientation flips the sign of the integral. All right. Okay, now examples of surface integrals. Just a quick revision here, just a quick reminder. So flux across the surface. I mean, what do we use all these forms for? Remember, the gradient is a one form. Remember, we talked about in other videos flux across surfaces. All right, so let the submanifold S contained in R3, for argument's sake, be a two-dimensional surface with a normal vector field N. Okay, a vector field F on R3 corresponds to a one form F flat. I'll be getting into that in a separate video. I'm not going into it now. Save to flats and sharps, flats lower, sharps raise. In terms of tensors, that's using the metric to lower the indices. So you go from a vector to a form, to a K form, one form, sorry, from a vector to a one form. Whereas with sharps, you're raising. Same thing, you're going from a one form back to K form, from a one form back to a vector. Sorry about that. Okay, so via the musical isomorphism, okay? But that's a separate video, I'm not doing that here now. So the flux of F through S is the integral of omega over S, that's the submanifold on the right of the previous slide, is the integral over S of F dot dn dA, all right? Okay, where omega is F flat, all right? Because omega is a form, a one form, and you're lowering it through the flat, hence F flat. All right. Integral of a two form on a surface. So let omega equals h of xyz, function of h xyz, dx wedge dy, wedge dz. If S is parameterized as f of uv equals x of uv, y of uv, z of uv, and this is what I did in the previous video. All right. Then we can take that surface embedded in R3 and take it back to a 2 form over which we can easily integrate over 2 variables instead of 3. All right? So the pullback of omega under the map F becomes H f of uv, the variables with which we parameterized our surface. Okay, so surface is x, y, z in 3 dimensions. It's now become a 2-dimensional surface by parameterizing in terms of the 2 variables u and v. And then we can integrate that. So it's h of f of uv, the determinant of the Jacobian matrix, du wedge dv. Okay, so the integral becomes the integral of omega over s is equal to, this is the important thing, the integral of the pullback of omega under the map F over u, which is, as I've just said in the previous slide, is that. Another thing I have a look at Stokes theorem. Stokes theorem provides a unifying framework for surface integrals in differential geometry. So for a k plus 1 dimensional manifold M with boundary partial M, Stokes theorem relates the integral of a k form, omega over partial M, to the integral over its exterior derivative, d omega over M. So the integral of omega over its boundary is equal to the integral of the exterior derivative of omega over the manifold M. All right? So for surfaces in R3, this reduces to the classical curl theorem or divergence theorem in vector calculus, where the exterior derivative of omega lifts the degree by 1. Okay, this is omega over the boundary. Okay, so it's taking a volume integral over a volume to an integral over a surface, if you think in terms of divergence theorem and so on in vector calculus. All right, geometric interpretation. So the surface S is parameterized by F, mapping k-dimensional points in U to the n-dimensional target space, so going from the open set U to the manifold M. Okay. A k-form omega measures the density of a certain geometric quantity like area, volume, or flux over the surface S. Okay, and the pullback of omega under the map F transports the measurement of omega from the surface S back to the parameter domain U. Right? And in the last video, we saw how that made our life integrating the function involved very, very easy. Integrating the form involved very, very easy. So the integral sums up the contribution of the pullback of omega under the map F over U, which corresponds to the integral of omega over S. We'll get into that in a little bit more detail, but here's the beauty of it all, right? The integral, the integral of omega over the submanifold is equal to the integral of the pullback of omega under the map F over U. As we saw in the previous video, how we went from 3 dimensions down to 2 and how it made the job of integrating the form omega or its pullback version much easier. And these two things give us the same result. They are equivalent. They give us the same result. And that's the beauty of this pullback process. It respects this invariance, this underlying invariance. So, okay, so here we are again. We've got our map F from the open set U contained in RK into the surface S contained in M. Okay, the manifold M is Rn. The manifold here U is RK in RK. All right, we have point P maps to a point F of P under this map. All right, we have on S, we have the coordinates x1, x2 up to xn because n-dimensional manifold. And on U here, we have the coordinates from U1, U2 up to K. Okay, it's a K-dimensional manifold here. And we have the cotangent space. So what we have here is a K form. It's pulled back to a K form over here, okay, under the map F. And that pullback preserves the K form, preserves its degree, that is, from here to here. Talk a little bit more about that. So some key properties, linearity. If omega and eta are K forms and A and B belong to the reals, then the integral over S of A times omega plus B times eta is just the integral of each of the individual forms, K forms, times a constant, separated or integrated together. So the integral of the sum of those is the same as the individual integral of each. Change of variables. If f is a map from surface 1 to surface 2 as a diffeomorphism, then the integral of omega over S2 is equal to the integral of the pullback of omega under f over S1. S1 being u in our case, and S2 being s for this video anyway. So I'll just say something about it. So in differential geometry, a change of variables using a diffeomorphism, that's f, which is a map from S1, surface 1 to surface 2, involves transforming integrals or differential forms defined on one manifold, S1, to another manifold, S2, using the smooth invertible map f. Okay, so far so good. So, all right, but what does all that mean? So it preserves a differentiable structure, allowing computations on S1 to correspond smoothly to computations on S2. And that's the beauty there of the diffeomorphism. It preserves the differentiable structure so that computations on both can be carried out and carried over from one to the other. All right, invariant under pullback, surface integrals respect the pullback under smooth mappings. So surface integral on one surface is under the pullback map equal to the integral on the surface of the other. Beautiful. Right, summary. Surface integrals on manifolds using differential forms provide a powerful general framework to integrate over submanifolds of arbitrary dimensions. This approach is intrinsic, that's independent of coordinate systems, and elegantly extends the classical calculus to curved spaces. Now, the pullback is a key tool translating the differential form to the parameter space of the submanifold. All right. So going from the right there back to the left. Okay, enabling the integral to be computed explicitly. Now, the framework, this is central to modern geometry, physics, like electromagnetism, fluid dynamics, and topology. Okay, so here we go again. Let's just have a look at this. Here's our K-form here. It could be any combination of these Q's and combinations of these dx's. All right, so long as they're all of K dimensions. So you could have any number of these strung together, Qi1ik times dx1 dxk plus Qi2 I3 times dx2 wedge dxik or something. You can have that linear combination, as I did in the video prior to this. And then the integral of omega over S here is equal to the integral of the pullback of omega under the map F to here, integrated over the domain U, over the values in U. All right, and to do that, we're substituting, we're pulling back these scalar functions Q by putting in the map F here in its place. So it's Q composed of F, all right, and then times the determinant for the transformation here from one coordinate system to another, times the wedge product in the new coordinate system. That's the U's. All right, I hope that's okay. Perhaps I can pull that up there just while I talk. So I hope that's okay with everyone. I hope that's clear. I look forward to any comments you wish to make. I hope if you liked the video and you found it useful that you will push the like button. And I implore you, please push the like button. Yes, you want to do it, go and do it. If you will, subscribe. I greatly appreciate that. It's up to you, of course, though. If you do find it useful, hopefully I'll see you again in the next video. So everybody take care. And as we're approaching Christmas, Merry Christmas, Happy New Year to everyone. And I hope to see you in future videos. All right, take care, everyone. Bye.